Welcome to a deep dive. Today, we're really getting our hands dirty, metaphorically speaking, looking at building construction. We're diving into this really comprehensive handbook.
Yeah, it's quite the volume, packed with everything from basic principles to, complex techniques and the regs that shape our built environment.
Exactly. So our plan is to sort of cut through all that density, pull out the key stuff, maybe find some surprising details.
I'll basically give you a shortcut to understanding, how the buildings around us actually go up and stay up.
Yeah, forget memorizing code sections. We want to explore what's critical, why it matters, and maybe change how you look at, the walls and floors you see every day. Okay, let's get into it.
Right. Where do we start?
Well, the handbook kicks off right at the beginning, defining the built environment, basically everything human-made around us. It mentions primary and secondary elements in buildings, and stresses things like regulations, surveys, documents right from the get-go.
And that documentation point is huge, isn't it? Construction drawings aren't just pictures. They are the absolute core language of any project.
So how detailed are we talking? I know there are different kinds.
Oh, incredibly detailed. You've got elevations showing the outside look, doors, windows. The handbook says minimum scale 1.100 for those.
Okay, and sections. They're like cutting the building open vertically.
Exactly. They show the inside, how things are constructed, floor meets wall, roof structure, that sort of thing. Needs more detail, so minimum scale 1.50 usually.
But you need even more detail for specific bits.
Definitely. That's where component drawings come in. They focus on individual manufactured items like a specific window unit or a beam connector. Scale can go from 1.100 right down to 1.1 actual size.
Wow. And assembly drawings put those components together.
Yeah, showing how items fit together. Scales like 1.20 down to 1.5 are common there. And the key thing, stressed in standards like BSEN, ISO 7519, is they must be annotated, dimensioned, cross-referenced, no room for error.
So precision is everything in the final drawings.
Yeah.
But also mention sketches. Are they just quick ideas?
Sort of. A sketch is more for a draft outline, visualizing 3D and 2D quickly. Can be freehand, can use tools, but even a sketch needs to be clear, have enough detail for its purpose, and crucially, get the proportions right.
Okay. And it briefly touched on projections like isometric, those 3D-looking views.
Yeah, using things like 45-degree lines to give that sense of depth. Useful visual aids.
Right, so all this careful drawing needs to connect with the real world. The handbook really emphasizes doing a site analysis before you even buy land.
Oh, absolutely critical. You wouldn't buy a car without checking under the hood, right? Same principle.
Makes sense. So what's on that checklist?
It's pretty thorough. You start with OS maps, get a proper measurement survey done. Then you look at what's actually on the surface, trees, slopes, rocks.
Visible stuff.
Yeah. And straight away, check with the local authority any preservation orders, conservation area, big implications.
Okay. And then you look underground.
That's maybe the most vital part. Investigating the subsoil. This means digging trial holes, maybe doing borings to see the soil layers, find the water table.
You need to know what you're building on.
Exactly. Plus, check flood risk, drainage, where existing utilities are buried gas, water, electric. Don't want to dig through those.
Definitely not.
And look for red flags, signs of filled ground, cracks in nearby buildings suggesting subsidence. And finally, just consider the neighborhood. Does the proposed building fit the scale and character?
Subsoil sounds key. How do you investigate deeper than just a shallow pit?
Good question. Trial pits are fine for the top layer, visual checks. For deeper stuff, you might use a mechanical auger like a big drill.
Yeah.
Different types sometimes needs a liner or casing to stop the hole collapsing.
Okay. And sampling shells.
They're for grabbing samples from shallow to medium depths, but not in solid rock. Then there's wash boring.
Wash boring sounds wet.
It is. You use a jet of water or sometimes a bentonite slurry to break up the soil at the bottom of the borehole. The returning liquid carries the soil particles up.
Ah, so you get samples without bashing them with a drill bit.
Precisely. Less disturbance to the sample structure. Doesn't work so well in really coarse gravel or boulders, though.
And all this borehole data gets logged really carefully.
Absolutely. On standard forms, drawings, showing exactly where each hole was and what they found at different depths. The handbook suggests a grid pattern for the holes, maybe 15-20 meters apart, to get a decent picture of the whole site.
And here's something interesting. I saw the handbook gives a cost benchmark for all this digging and testing.
Yeah, that's a really telling figure. It says the cost of site and soil investigations should ideally not be more than about 1% of the total estimated project cost.
Only 1%. That seems low for something so fundamental. Get it wrong, and the whole project could fail.
It really underlines how valuable that investigation is. It's incredibly cost-effective insurance against major problems later.
So you've got your soil samples. What happens next? Assessing them.
Right. You need to classify the soil. Is it clay, sand, gravel, silt? Grade the particle sizes, and then test its properties like shear strength, how well it resists sliding, and consolidation, how much it compresses under load. Standards like BS 1377 cover all this.
They mentioned the SPT standard penetration test, something about counting blows.
Yeah, the SPT involves driving a standard sampler into the ground with a standard weight dropped from a standard height. You count the number of blows needed to drive it a specific distance.
And that number tells you.
It's a direct measure of the soil's resistance, which indicates its density or stiffness. For sands and gravels, say 0.4 blows means very loose, unstable. Over 50 means very dense, strong. For clays, 0.2 is very soft, 30 plus is hard. Needs expert interpretation, of course.
Okay. And they briefly mentioned a vein test for soft clays and bulk density for designing retaining walls.
Yep. Vein test measures shear strength directly in soft, cohesive soils. Bulk density, just the mass per unit volume, is crucial when you're calculating the weight of earth pushing against something like a retaining wall.
Right. So all that ground knowledge feeds into the next stage, setting out, actually marking the building on the ground.
Precisely. Transferring the design from the drawings onto the site usually starts with establishing a baseline often dictated by the local authority, like the building line. Everything gets measured from that.
And then setting out the trenches for foundations.
Yeah. You need to mark the exact position, width, and depth. This is often done using profile boards, timber frames set up well clear of where you'll be digging, maybe 2 meters away minimum, so they don't get knocked.
And these boards help guide the digging.
They do. You fix a horizontal crossboard on the profile at a specific level related to a site datum point. Then you can use a measuring rod called a traveler or a surveying level and staff to check the trench depth as you dig. The width of the foundation or wall is marked on the crossboard too, usually with nails or saw cuts.
What about setting out a framed building, like steel or concrete columns? Is that different?
It's often based on a grid on the drawings. The grid intersections usually mark the center points for the column foundations. You'd use surveying instruments, like a theodolite, to set out this grid accurately from the baseline, marking points with pegs. Again, you'd use offset pegs or profiles, clear of the excavation work itself.
And getting the levels, the heights, right, is obviously crucial for all this.
Absolutely fundamental. On-site, you usually work from a temporary benchmark or TBM, some fixed point, like a manhole cover, because the official ordnance datum, the national height reference, may be far away. You use leveling instruments like tilting levels or, more commonly now, automatic levels with a measuring staff. Automatic levels are easier as they self-level internally.
Okay, so planning done, ground checked, layout marked. Now, the actual foundations. And the handbook brings up trees as a foundation issue.
Oh, yes, big time. Especially broadleaf trees like oak, elm, poplar, and willows are very thirsty. In dry weather, their roots can suck huge amounts of moisture out of clay soils, causing the ground to shrink.
Which makes the foundations sink or settle unevenly.
Exactly, leading to settlement and potentially nasty cracks in the building.
And the opposite can happen if you remove a tree.
Precisely. If you take out a big tree that was drying the soil, the ground can rehydrate over time, swell up, and push the foundations upwards. That's called heave. And the effect of these trees can reach quite far. The handbook mentions up to 30 meters.
30 meters, wow. That's further than you might think.
It is, which is why you have to consult the local authority if significant trees are nearby. You might need special foundation designs, maybe with a compressible layer underneath to absorb heave, or even suspended ground floors that don't sit directly on the potentially moving soil.
So trees are a big factor. And you mentioned severe cracking often points to foundation failure.
It's often the main symptom, and it's not just cosmetic. Bad cracks affect stability, let rain and drafts in, waste heat, reduce sound insulation, and obviously hit the property value.
So how do you figure out why a wall is cracking? It sounds complicated.
It can be. The handbook suggests a systematic check. Look for external causes like tree roots, soil movement. Consider climate effects, expansion and contraction, moisture problems, leaks, damp-proof course issues, vibration from traffic or construction, and finally, changes in the materials themselves, like steel corrosion or timber decay. It's detective work.
Okay. So assuming you understand the ground, what kind of foundations does the handbook talk about actually building?
Several main types. Raft foundations are like a big slab covering the whole footprint, spreading the load, good for weak soil or where column loads are heavy and close together.
Cantilever foundations.
They're used sometimes to avoid putting pressure right on a boundary line or over an existing underground service. You sort of cantilever the foundation base inwards from a supporting point within your site.
And piled foundations, for when the good ground is deep down.
Exactly. You bypass the weak upper layers and transfer the load down to stronger soil or rock below. Displacement piles or driven piles are hammered or vibrated in, pushing the soil aside. They're driven until they hit a certain resistance called the set.
And different hammers for driving them.
Yeah, simple drop hammers, single-acting steam or air hammers where gravity does the downstroke, and faster double-acting ones where power drives it both up and down. Different weights and blow rates for different pile types and ground conditions.
What about holding back earth on slopes? Retaining walls.
It mentions crib retaining walls. These are made from interlocking concrete or timber units forming boxes or cells. You fill these cells with stone or soil, and the weight of the fill helps the wall resist the earth pressure behind it.
I saw a diagram about calculating earth thrust. Sounds complex.
It involves understanding the soil's properties, like its angle of repose, and the wall height to figure out the force the retained earth will exert. Critical for designing a stable retaining wall.
Okay, let's go deeper still. Basements. How are they built, especially deep ones?
Well, a basement is just a story below ground level. Deep basement construction is complex stuff, often done within a temporary cofferdam or supported excavation. Techniques like diaphragm walls can be used, supported permanently by ground anchors drilled into the surrounding earth, or by the basement's own floor slabs acting as props. Temporary support might use big steel lattice beams.
And how do you stop a basement acting like a boat and floating up if the water table is high?
Big risk, yeah, flotation. The handbook mentions using vertical ground anchors going down through the basement slab into the ground below to literally tie it down.
And the number one basement worry, waterproofing. How's that done?
3 main ways described. One is relying on dense monolithic concrete. But this needs perfect materials, mixed design, workmanship, compaction, control of cracking, you name it. A low water assessment ratio is key, around 0.5 or less, ideally.
So possible, but difficult to guarantee.
Very, and even then, it might not stop water vapor. So the other methods are more common. Tanking, which means applying a waterproof membrane like asphalt or plastic sheets, either inside or outside. And drained cavity systems, which create a space behind the inner wall lining to collect any penetrating water and drain it away safely.
And basements need insulating too, right? Thermal performance.
Absolutely. They're part of the building envelope, so building regs approved Document L and standards like BSEN ISO 13370 apply, setting targets for U values to limit heat loss.
Okay, foundations and basements sorted. Moving up to the main structure. Concrete work above ground.
Right. The handbook breaks concrete work down into mixing, transporting, and placing. Even simple drum mixers are designed to rotate to stop the sand, aggregate, and cement separating, that's called segregation, ruins the mix.
And the basic steps for building with reinforced concrete.
It's a sequence. Assemble the formwork, the mold, prepare and place the steel reinforcement inside it, pour and compact the concrete. Then, once it's cured enough, strike or remove the formwork.
What about using that profiled steel decking for floors as permanent formwork?
Yeah, that's very common for composite floors. The profiled galvanized steel sheets act as the formwork, and the indentations create a bond with the concrete poured on top. The steel then works with the concrete structurally, providing tensile strength, though you still need reinforcing bars within the concrete slab itself.
And for columns, the vertical bits.
That needs column formwork. A strong vertical mold designed to resist the outward pressure of the wet concrete. You use clamps or yokes around it, usually metal these days. Often, a small concrete kicker is cast first on the floor slab to position the column formwork accurately and seal the bottom joint.
What about precast concrete frames? Factory-made structures.
Often used for single-story or lower-rise buildings like industrial units or supermarkets. Columns, beams, maybe even floor units are made in a factory, shipped to site, and assembled. Can be quicker on site. Often based on standard component sizes. Custom precast gets expensive because of mold costs. Fixings are usually bearing connections or bolted steel plates.
Now, pre-stressed concrete. This sounds different from just putting steel bars in.
It's a really clever concept. Standard reinforced concrete uses steel to handle tension, the pulling forces, because concrete's weak in tension. Pre-stressed concrete deliberately puts the concrete into compression before it takes any load.
You pre-squeeze it. Why?
The aim is that when the actual working loads are applied, the stresses in the concrete remain compressive, which concrete is brilliant at handling. It means you can use the material much more efficiently, design longer spans or shallower beams than with ordinary reinforced concrete.
Ingenious. And two main ways to do it.
Yes. Pre-tensioning and post-tensioning. Pre-tensioning is usually factory-based. You stretch high-tensile steel wires or strands in a mold, then pour the concrete around them. Once the concrete hardens, you release the tension. The bond between the steel and concrete holds the compression in.
Okay. And post-tensioning.
That's often done on site. You cast the concrete with ducts or tubes running through it. After the concrete gains strength, you thread steel tendons through the ducts, stretch them with hydraulic jacks, and then lock them off with mechanical anchors at the ends. The ducts are usually then grouted up for protection and bond.
Fascinating stuff. Okay, shifting materials, suspended timber floors.
Yeah, the traditional joisted floor. Joists span between walls or beams carrying floorboards or chipboard panels. They usually sit on timber wall plates on top of masonry walls or in metal joist hangers.
And there was even a rule of thumb for sizing joists.
A very simplified one for basic domestic floors, yeah. Depth in millimeter equals span in millimeter divided by 24 plus 50 assumes certain conditions like 50 millimeters width and 400 millimeter spacing. Just gives you a rough idea of how depth relates to span.
And strutting between joists.
Essential for longer spans, over about 2.5 meters. It's rows of bridging pieces, often in a herringbone pattern, fitted between the joists at midspan, stops them twisting or vibrating too much, which could crack the ceiling underneath. Max span mentioned is 6 meters.
Lateral restraint for walls came up again here. Tying floors into walls.
Yes, ensuring the floors provide horizontal support to stop walls, especially gable end walls, from bulging or leaning outwards, usually done with galvanized steel straps fixed to joists and built into the brickwork. Lack of good restraint was apparently a common issue in older buildings.
Okay, back to concrete floors. Reinforced concrete suspended floors.
The handbook notes that simple flat slabs get less economical over about 5-meter spans. Using beams within the slab allows longer spans but makes the formwork deeper and more complex to build.
Ribbed floors and hollow pot floors sound like ways to make concrete floors lighter.
Exactly. Ribbed floors use special molds like waffle or trough shapes to create voids underneath. Reduces the self-weight of the concrete so you can span further or carry more load. The troughs can be handy for running surfaces, too. Hollow pot floors are similar, but use permanent formers, hollow clay, or concrete blocks between concrete ribs, giving you a flat soffit ready for plaster.
And precast concrete floors as an alternative.
Yeah, factory-made planks or units. Big advantages are speed on site, no formwork needed, minimal curing time before you can work on them, and generally better quality control from the factory environment.
Disadvantages.
Less design flexibility on site, harder to form awkward shapes or large openings without needing extra poured concrete sections, and they demand very accurate site dimensions for the supporting structure.
Finally, for structures, raised flooring came about because of computers, right?
Pretty much. Developed mainly in the 70s for offices needing lots of cabling under the floor. It's basically floor panels, often 600 millimeters square, sitting on adjustable pedestals, creates a void underneath for wires, data cables, even air conditioning ducts. Pedestal heights vary enormously, from just 30 millimeters up to 600 millimeters or more.
Okay, structure done. Let's look at the building's skin walls, openings, roofs.
Starting with wall features. Plinths, those projecting bases at ground level, needs durable, frost-proof bricks, and the joints mustn't hold water.
And corbels, projecting bits higher up.
Yeah, often decorative, sometimes structural support. Rule of thumb for structural corbels is the projection shouldn't be more than a third of the wall thickness it sits on.
Cavity walls. Standard now, aren't they?
Very much so. Typically a 50-75 millimeter gap, sometimes wider up to 300 millimeters with special ties, usually sealed top and bottom, not ventilated. Stainless steel or non-ferrous wall ties are preferred now over older galvanized ones, less risk of corrosion.
Parapets, those low walls around flat roofs or balconies.
Tricky things because they're exposed on 3 sides, front, back, and top. Need really careful detailing to keep water out and ensure they last.
Keeping water out, damp-proof courses, DPCs. Critical stuff.
Absolutely vital barrier against rising damp from the ground. Lots of materials mentioned: bitumen, felt types, modern plastics like polythene, LDPE, polymer-modified bitumens. Pitch polymers used to be common but had health concerns.
What makes a good DPC?
Needs to resist decay, be tough enough not to tear easily, bond okay with mortar, and handle a bit of movement. Crucially, joints must be lapped at least 100 millimeters and sealed, and it has to connect properly with the floor damp-proof membrane, DPM. Mastic asphalt is very durable but needs a keyed surface. Even 2 courses of dense engineering bricks can work as a DPC because they absorb so little water.
What if you have rising damp already? Treating it.
Chemical injection is common, drilling holes and injecting fluids that line or block the pores in the brickwork. The handbook stresses it's a control method, not always a complete cure. Some vapor might still get through. BS 6576 is the standard. Failure isn't always the DPC material itself. Often it gets bridged, like soil piled up outside or plaster inside going down past it.
Load-bearing brick walls, this strength isn't just about the bricks, is it?
No, definitely not. Sizing depends on thickness, brick strength itself, which varies massively, mortar strength, how tall and thin the wall is, slenderness ratio, and whether the load is applied centrally or off-center, eccentricity, all covered in standards like BS 5628 or simplified in approved document A.
Arch construction looks tricky for damp proofing.
It is. An arch supports itself once built, usually over a temporary center. Putting a standard DPC over the top is difficult because water running down the cavity can bypass it. That's why proprietary cavity trays, often shaped metal or plastic, are used to catch water within the cavity above the arch and channel it out through weep holes.
Okay, moving to openings. Windows and doors. Head, jambs, sill.
Right. The jamb sides need attention. In cavity walls, you need to prevent moisture crossing the cavity there. The handbook mentions checked reveals a stepped profile in the brickwork at the jamb being needed in areas with severe wind-driven rain exposure, like the West Coasts.
Lots of window types mentioned.
Casement windows are very common in the UK. Modern ones have to perform really well thermally, Part L regs, and acoustically, Part E, plus resist wind and rain. Designs are often adapted from places like Scandinavia now, achieving low U values and good sound reduction.
Sliding sash windows, too.
Yep, vertical or horizontal sliders. Pivot windows rotate. Bay windows project out and have wall support below sill level. Oriel windows also project out but are supported higher up, maybe on corbels.
Choosing glass more to it than just being clear.
Oh, yes. You've got clear, patterned translucent for privacy, wired glass for fire resistance. Choice depends on wind load, vision needs, privacy, security, fire regs, and just how it looks.
Glazing is fitting the glass in the frame.
Into a rebleed, usually sealed with putty or held by beading strips. Different putties for timber versus metal frames. BS 6262 covers the standards.
Double glazing is pretty much essential now.
For energy efficiency, yes. 2 panes with a sealed gap, air or argon gas, 620 millimeter typically. Cuts heat loss, cuts noise. Metal frames need a thermal break to stop heat conducting through the frame itself. And good weather seals are vital on opening parts. Low emissivity, or low E, glass has a special coating that lets sun heat in but reflects room heat back inside.
Safety glass is crucial in some areas, isn't it?
Absolutely. Doors, low-level glazing, anywhere someone might fall against it. Needs to either break safely, like toughened glass into tiny bits, or be hard to break through, like laminated glass, which holds together. Standard annealed glass is too dangerous in those critical locations.
Moving quickly to doors.
External doors are generally thicker, more robust than internal ones. Need to handle weather, security, insulation, timber, metal, steel options. Frames have standards too, like BS 4787. And ironmongery hinges, locks, handles are obviously key.
Fire doors are rated for safety.
Yes, usually FD 30, 30 minutes resistance, or FD 60, 60 minutes. Resistance covers integrity, stopping flames and hot gas passing, and insulation limiting heat transfer. Standards like BS 476 apply.
And it's like FD30s means it also resists smoke spread.
Right up to the roof now. What's the layer under the tiles?
The roof underlay, often called sarking felt, or more commonly now, a breather membrane, plastic sheeting. It's a second line of defense against wind-driven rain or snow getting into the roof space. Modern plastic ones are lighter, but some types can increase condensation risk if not properly vapor permeable. Vapor permeable ones, to BS 4016, are generally preferred.
Tile types. Plain versus single lap.
Plain tiles are small, need a double overlap, so more tiles, more battens, more labor. Single lap tiles are larger, often interlocking, cover more area per tile, so lighter, quicker, fewer battens.
Plates are a natural classic.
Beautiful, durable material, split thin, used on pitches usually over 25 degrees, laid with a double lap like plain tiles, fixed with nails either near the top head nailing or near the middle center nailing, depending on slate size and exposure, to stop them rattling or lifting in wind.
Energy saving in roofs. Cold deck versus warm deck.
Key distinction for insulation. Cold deck means insulation at ceiling level, joist level. leaving the roof space itself cold and needing ventilation. Warm deck means insulation laid over the rafters, directly under the roof covering, keeping the roof structure warm and reducing ventilation needs. Preventing condensation is vital. Either use a vapor control layer on the warm side of the insulation or ventilate the cold space effectively. Vapor Check plasterboard can help act as that vapor barrier.
And lateral restraint needed again for gable walls at roof level.
Yes, steel straps tying the top of the wall into the roof structure to resist wind loads, similar to how floors restrain walls lower down. Some roof constructions provide inherent restraint, though.
Okay, that's the building shell covered. Now the systems inside and around it, services and finishes.
The building's arteries and veins, starting with drainage. Handbook splits water into surface rain, waste, sinks, baths, and foul soil, toilets.
Subsoil drainage, when's that needed?
If the ground's naturally waterlogged, building Red C2 might require it to protect the building fabric and foundations, usually perforated pipes in a gravel-filled trench, only really economical up to about 1.5 meters deep.
Basic principles for designing drainage runs.
Keep it simple, efficient, economical, must be laid to a proper gradient so it's self-cleansing, the flow carries solids away, needs to be watertight, obviously, and meet Building Regs Part H.
And access points are needed for clearing blockages.
Yes. Inspection chambers for shallower depths, up to 1 meter invert level, common in houses. Manholes for deeper drains, over 1 meters.
Pipe sizes and gradients sound critical.
Absolutely. Minimum 100 millimeter diameter for anything carrying waste from a WC. Otherwise, it gets complicated with discharge units and hydraulics, BSEN 140562, but simpler rules like a McGuire's rule can give a basic guide for gradients needed for self-cleansing flow.
Hot water systems. Indirect seems standard now.
Especially with central heating or in hard water areas. The boiler heats a primary circuit which passes through a coil, heat exchanger, inside the hot water cylinder. This heats the stored domestic water indirectly, preventing scale buildup from direct heating of hard water. Cisterns feeding these systems need insulation against freezing.
What was that primatic cylinder?
A clever, simpler type of indirect cylinder for smaller systems uses internal baffles and airlocks to keep the primary and stored water separate within the same tank, saving some pipe work. Less common now, I think.
Electrical supply. Safety first, always.
Top priority, proper earthing, preventing leakage, stopping fires. External meter boxes are preferred now for easy access for readings or emergencies.
And the fuse box is now a consumer control unit.
Or just consumer unit, yeah. It's the distribution board. Has the main switch, bus bars distributing power to individual circuits, and protection either fuses, older, or MCBs, miniature circuit breakers. Crucially, modern ones must have RCDs, residual current devices, protecting circuits, especially sockets, for shock protection. They trip instantly if they detect tiny leakage currents to earth.
Cable sizing must be calculated carefully.
Essential to prevent overheating, based on the maximum current expected and allowable voltage drop. Handbook gives typical minimum cable sizes for domestic circuits.
Ring mains for sockets are typical.
Yes, the standard UK system for sockets. A 32 amp circuit loops around the area, connecting sockets in a ring. Theoretically unlimited sockets, but regs limit the floor area per ring, 100 meter Margochardy. Spurs allow adding 1 or 2 sockets off the main ring.
Lighting circuits are separate.
Yes, lower current, usually 6 amp protection, wired differently, loop-in method. Need multiple circuits so one fault doesn't plunge the whole house into darkness.
And accessories, switches, sockets, bathrooms.
Switches typically 5 amp rated for lighting, lamp holders, and yes, bathrooms have specific rules. Pull cord switches must be used to avoid touching switches with wet hands. No standard sockets allowed either, only special shaver sockets.
Glass supply. Pipes and safety.
Steel or polyethylene pipes. Gas fires, under 60 kilowatt domestic, covered by Building Regs Part J. Need a flue to take combustion products away safely, could be a chimney, special blocks, or a dedicated pipe. Balanced flues draw air from outside and vent outside directly, very common now.
Services fire stops sealing holes where pipes go through firewalls.
Critically important. Building regs, approved Doc B3 demand proprietary seals where services penetrate fire-rated walls or floors. These often use intumescent materials like collars around plastic pipes that swell up massively in heat, sealing the hole and maintaining the fire separation for a set time, maybe 2 or 4 hours.
And open fireplaces.
For solid fuel, under 50 kilowatt, basic parts, hearth, recess, chimney, flue, terminal. Big issue is combustion air fireplaces need a lot of air, traditionally sucked from the room, causing drafts. Regs now encourage dedicated air supplies, often ducted from outside, for safety and efficiency.
Phew. Okay, that's a lot of the how-to. Let's quickly touch on some overarching rules and accessibility environment stuff.
Right, the regulatory framework. Lots mentions CDM regs for site safety, specific building regulations like Part L, energy, E, sound, H, drainage, J, combustion, K, safety glazing, A, structure, M, access, plus British and European standards, BSEN.
What does the kite mark symbol mean?
It's a certification mark from the British Standards Institution, BSI. Assures a product is manufactured and tested consistently to the relevant BS standard. Though remember, BS recommendations aren't law unless specifically referenced in the building regulations.
Planning permission again. Some things don't need it.
Small extensions, permitted development, might be exempt based on size limits, often related back to the house's original 1948 volume. Bizarrely. Small porches, too. But you always need specific consent for work on listed buildings or demolition in a conservation area. And dealing with contaminated sites is a big planning issue now, too.
Access for disabled people, building regs, Part M. What are some key things?
It covers a lot. Handrails needed for level changes. Guarding around hazards, maybe tactile paving near their low windows. Wheelchair-accessible entrances, minimum widths, clear space beside the door handle, vision panels at the right height. Similar rules for internal doors, slightly narrower minimum width. Corridors need minimum clear widths, and requirements for lifts or alternative access like stair lifts or platform lifts.
And testing the finished building. Energy efficiency, air tightness.
Yes, commissioning reports for heating ventilation systems. Air tightness testing is common now for new builds to check for leaks using smoke or pressurizing the building. Helps identify thermal bridging issues too, where heat escapes easily.
Sound insulation, Part E.
A big focus, especially between flats or terraced houses. Different requirements for lightweight framed walls versus solid masonry. Separating floors between flats need testing for both airborne sound, voices, music, and impact sound, footsteps. Different constructions for concrete versus timber floors.
And contaminated sites, again, cleanup methods.
The traditional way is just dig it up and take it away, dig and dump. But finding landfill sites is hard, and it's costly for deep contamination. So alternative methods, physical, chemical, biological treatments on site, are increasingly used where possible.
Wow. Okay, so we've gone from the soil under our feet through foundations, structures, walls, roofs, services, right up to the rules governing it all. It's a lot.
It really is. It shows just how complex building construction is, even for relatively simple structures.
Yeah.
Every little detail matters, the type of wall tie, the water content in concrete, the overlap on roofing felt.
Yeah, seemingly tiny things have big impacts on safety, durability, how warm the building is, how quiet it is.
Exactly. And it's this constant interplay, isn't it, between the design ideas, the actual properties of the materials, the quality of the workmanship on site, and this whole complex web of standards and regulations that everything has to comply with.
It all has to come together. So thinking about the sheer volume of connected details we've just skimmed through from this handbook, all needed to get even a straightforward building right.
Mm-hmm.
What hidden layers of complexity, what unexpected challenges might be lurking in the construction of the really big, complicated structures we use every day without a second thought?